Okay, we'll start off class with just a real quick, what we're doing this week. So we're lecturing on Chapter 6. Tuesday you need to finish the, what do we call that, spectroscopy lab? Which means if you haven't done it, you need to have those graphs done. On Wednesday, we'll still probably be on Chapter 6. And then on Thursday, we're looking at starting a new lab. Or I have an extra thing that we might try. And of course, Friday you have day off.
On Thursday, we're doing Ionization.
Okay. And then Monday and Tuesday of next week, the key is that we're going to have probably a test on Tuesday on chapters 5 and 6. So that's kind of the week at a glance. Where we left off was we were talking about periodic trends. And the reason these periodic trends exist is due to the shape of the periodic table. Or they're kind of based on the shape of the periodic table, but they really all resolve down to understanding the quantum mechanics and the locations of the electrons. And so we looked previously at size, and we said that the trends we're going to look at are, for instance, down a column, and we could look across a row. And then we also looked at the size of cations versus the neutral atom, and the size of anions versus a neutral atom. Now, does anyone remember what happens to the size of a molecule going down a column? If we compare, say, lithium versus, say, cesium. Which one's bigger? Yeah, cesium's bigger, so size increases down a column. And what about across a row if we compare lithium versus fluorine? Size. Let me show you guys where I want. Well, where did they put it? They did the first. Oh yeah, they put that in chapter 5. I was going to say the graph. Across a row, what's happening is Z effective is increasing, but the electron shielding is about the same. So we expect them to shrink or decrease across a row. What about cations versus neutral atoms? Which one's bigger? Cations are smaller or bigger? Cations are smaller, anions are larger. And then remember, the key part is I want you guys to fill in that because. I'll point out that there's a nice figure on page 187. In fact, you're going to note that I'm going to put references to figures on a lot of them. I've also got another PowerPoint slide set up. These are really just pictures from your book, but for instance, this gives you a size comparison so you can kind of see how much the size either increases or decreases. So notice that all the cations are smaller, and if we flip to the anion chart, there it is. Anions get, a good chunk bigger, maybe about a 75% difference. Let's see, this is the next one I want to talk about, so we won't go there. So keep in mind all of sort of what we have in have for trends. And think about the reasonings we're using, meaning we used Z effective equals Z actual minus the electron shielding. We've also used the fact that we know electrons repulse and that electrons and protons, of course, are attractive. These are the types of arguments we're going to use. So the next one we want to look at is ionization energy. And the goal for this is that eventually we can calculate or track all of the energy flow in a chemical reaction, and we can determine, if a reaction is exothermic or endothermic, and whether we have to supply energy for it to occur, whether we're going to get energy out of the reaction. And eventually we can actually calculate how likely or if the reaction is going to occur spontaneously. So what ionization energy is, and I abbreviate this IE, or really your book abbreviates it E for energy with a sub IE, meaning specifically we're talking about the ionization energy. So I need to train myself to write ionization energy that way. I got to be honest, it's not natural for me to write it that way simply because I'm so used to writing it the other way. So I'll try to train myself to be good. So ionization energy is basically the amount of energy required to remove an electron. Oops, required. From an atom. And so what we're looking at, for instance, is lithium going to lithium plus an electron. And it turns out that ionization energies are ionization energies are always positive. Because it always takes energy to separate charges. So where should I put energy on this equation? Should it go on the right-hand side of the equation or the left-hand side of the equation? If we have to add energy to the system, it takes energy, right? So that means that the energy term should go on that side of the equation. And the other way to think about it is if I take a look at lithium, I can write it kind of like this. Lithium is 1s2, 2s1, and what I'm really getting is 1s2. There's no electrons in the 2s, and an electron there in the reaction. So I can write it in terms of the atoms, which is sort of how we've looked at it before, or I can write it in terms of those electron shell configurations. So what we want to look at is basically two trends. What happens down a column? Do we expect ionization energy to increase or decrease? For instance, if I compare the ionization energy for lithium versus cesium. So think about it. It's the energy required to separate that electron. So what's the difference between separating or taking the electron from lithium and taking the electron from cesium? Pictorially, it's pretty easy. If I take a look at lithium, remember that electron is in that 2s shell. And if I take a look at cesium, how far down the periodic table is that? 1, 2, 3, 4, 5, 6 rows down. And so cesium is actually 1, 2, 3, 4, 5, 6. There's my 6s, and I'm taking that electron away. Which electron is easier to remove? Cesium's. Why? Yeah, it's farther from the thing. So down a column, ionization energy decreases. And the reasoning behind that is because the electrons are further away from the nucleus. It's kind of the same exact reason because the size of the atom is increasing, right? The electrons are further away from the nucleus, therefore easier to remove. And remember, you can think about that ionization energy as basically two magnets. You know, how easy is it to separate two magnets? The further apart they are, the easier it is to separate them, right? If the magnets are actually stuck together, especially with the new, nice, good rare earth metal magnets, those are almost impossible to pull apart once they're stuck together. What about across a row? So here we're talking lithium versus, say, fluorine. And so again, lithium is still that same 2s electron. But fluorine now, you know, we've got some 2p orbitals in there too. So this is the 2s, 2p, and it's got 7 electrons in that outer shell. So how easy is it to remove, or which one is easier to remove? So across a row, ionization energy oh, it increases. I was trying to look, so it increases because the electrons are closer to the nucleus. And we know that because we know that the size of an atom decreases across a row. Therefore, it's harder to remove. So if we take a look at what happens in those periodic trends, we can find out some additional information too. So here is a picture or a plot of the ionization energy versus atomic number. And notice which ones have really high ionization energies. What's in common about all those elements? What am I talking about? Jesus crikey, Jay. Noble gases have the highest ionization energy because it's hard to remove an electron from a completed orbital or a completely filled orbital. Which ones have the easiest or the lowest? So notice the lowest is the alkali metals because the electron is alone, therefore easy to remove. And then notice what happens is if we're going across a row, the ionization energy is increasing. But it's kind of funny because you get these little blips. For instance, if we take a look at, lithium, that's beryllium next to it, and then there's a little drop down, and then it goes a couple more elements and a little drop down, and then it goes up a couple. Notice that those little blips occur going from an s to a p orbital and from a half-filled or a p orbital to a half-filled p orbital. So remember, we mentioned that half-filled orbitals, for instance, right here, that's going from something that looks like this to something that looks like this. Having those half-filled orbitals shifts the energy levels. That's what makes a lot of these calculations, if you really have to do the calculations, difficult. But, we can look at it in terms of just a rule of thumb, which is a half-filled orbital is lower in energy by a small amount than either slightly more filled or slightly less filled energy orbitals. And so we get those blips. Same thing here. If you look, this is the d block, and so here's that half-filled d orbital. Here's the transition from d to p orbitals. And so you can follow those trends along pretty easily and see how the energy levels are corresponding. Now, that's for removing one electron from an element, right? What do you think happens if I try to remove more than one electron? So, removing multiple electrons. So, for instance, if I take lithium and I go to lithium plus an electron, that's, the first ionization energy, so we're going to call that IE1. But if I take that lithium positive cation and I try to make a lithium plus 2 cation plus an electron, that's my second ionization energy, meaning the energy required to remove the first electron, the energy required to remove the second electron. What happens to that energy, do you think? Yeah, so this is always higher. And if we take a look at a chart, this is page 191 in your book. I'm not going to reproduce it. But if we take a look at that and you make a reference to it, where is it? Right here, notice that if we take a look at these ionization energies, unfortunately they didn't use lithium on it. Well, that's annoying. So if I take a look at sodium, notice that and sodium is about the same as lithium, right? Notice that it's really easy to remove that first electron from sodium, right? But to remove that second electron from sodium is really tough. So the first one's easy, second one's tough. Notice for magnesium, it does increase also, but that there's a huge jump going from the second. So that's the first electron. Oh no, I'm sorry, this would be the first electron. Here's the second one. There's, for some reason, a huge jump in the third electron for magnesium. So let's take a look at that. Oh, well, they kind of have it there, but that's okay. We're going to draw it out ourselves because we need practice. So notice that if I take a look at sodium, that's that first ionization energy. So I'll redo this since I don't have lithium in there. That's 496 kilojoules per mole. Notice that that's going from a 1s2, 2s2, 2p6, 3s1. That's the electron I'm removing, right? Now if I take a look at sodium plus, going to sodium 2 plus an electron, that ionization energy for that second electron is a huge amount more, 4,562 kilojoules per mole. 1s2, 2s2, 2p6. Notice that that's the electron I'm removing it from. So notice that here, this is just a lone electron. This is an electron in a completed orbital shell, which is approximately like a noble gas. Therefore, it's extra stable, because we know the noble gases don't form reactions, so they're not likely to lose electrons. That's why it takes so much energy. So they're extra stable, therefore they don't give up the electron easy. And if we take a look at magnesium, and I'm just going to draw this as a series, just because I'm too lazy to keep drawing it all the way. Notice that magnesium is 1s2, 2s2, 2p6, 3s2. So here I'm removing it from a new shell. And here it's 1s2, 2s2, 2p6, 3s1. Again, here it's just the new shell. So getting to magnesium 2 plus is easy. And then I ran out of room, so I'll put this one down here. But magnesium 2 plus, to go to magnesium 3 plus, notice that this is from a completely filled shell. So again, that looks like a noble gas. And so for the first one, it takes 738. For the second one, it takes 1,451. And for the third one, again, there's that huge jump, 733. Now, don't memorize the values, obviously, but, you know, kind of remember the learning. So the idea is that removing electrons from completely filled orbitals is very hard. And so that's why you see those jumps on the chart. If you'll notice the chart here, the jump in this case for aluminum is to remove that fourth electron. And so the idea is that we know that sodium prefers to be sodium plus 1 because it doesn't take much energy. Magnesium is okay being magnesium plus 2 because, again, doesn't take much energy. Aluminum likes to be aluminum plus 3 because it doesn't take a lot of energy. And so you can see, like, for instance, by the time you get down to sulfur, holy heck, you know, there's no way you're going to get a sulfur that loses a ton of electrons. And so remember, part of the common charges is also due to that idea of getting those octets. And so removing an electron from that octet is super hard. Let's see. I don't even know what that's for. This is for our next one that we're going to talk about. So let's go back to the other slideshow. So for ionization energy, decreases down a column, increases across a row. There's small blips for half-filled orbitals. And remember that you can have second and third ionization energies, and that the big jump happens when you're taking an electron from a completely filled shell. That would be sort of, if I had to write a 2-second summary, and I don't think I could write that in 2 seconds, but I certainly can say it pretty easy. Okay, so what's the opposite of removing an electron? Yeah, so we call that electron affinity. And so remember, our goal, for instance, is to understand how ionic compounds are formed. It's one of the reasons we're doing this. And we kind of looked at it already because it completes octets. But half the picture is ionization energy. And the other half of the picture is somebody has to gain an electron. That's called electron affinity. And that is the energy change that occurs when an electron is added. That occurs when an electron is added to an atom. So an example of that might be if I take fluorine and I add an electron to make fluorine minus. Then I would have my electron affinity down here. Now, electron affinity is one of those things where, depending upon which book you read, can be defined as a positive value, meaning the energy that or it can be defined as, well, okay, I should say it. So some books define it this way. So we're, adding the electron. Some people define it as the reverse, which is to remove an electron from an anion. Your book uses this, so that's what we're going to define. And so in this case, electron affinities are always negative, meaning we actually tend to release energy when we add an electron. Therefore, the energy should show up as being exothermic, meaning we release energy from the system. Now, some books are going to define it as the opposite, and you just have to remember to change the sign. The other odd thing about electron affinity is that electron affinities cannot be positive by this definition, because it would be impossible to add the electron. Some elements you literally just cannot add an electron to. For instance, if we take a look at most of the normal metals, for instance, sodium plus an electron just does not happen. And what that means is that we have to define EA as basically equal to 0 at that point, because if we can't perform the experiment, we can't measure the value. We know it's positive. We just don't know what value it is, because literally it's impossible to measure adding an electron to sodium because it just doesn't want that electron at all. And so you get a weird graph like this. And pay attention to the axes. Notice that they put the negative numbers on top. And so it's kind of a weird graph, because since when do we label the y-axis with the negative part at the top? That's strange, right? Notice for ionization energies, it was positive at the top, negative at the bottom. And so here, the way they do that is because the idea is that these elements gain electrons the easiest. And of course, down here, these are all elements that don't gain electron, elements that won't gain an electron. So electron affinity is a little bit more complicated than ionization energy, because the process is a little bit more complicated. And so really the part that we want to take from this is that generally halogens have the highest electron affinity, and alkali metals and the alkaline earth are basically 0. And we won't worry about any periodic trends too much beyond that. Realize that if you kind of look at it, you know, here would be oxygen. On the chlorine level, that would be sulfur. You know, so oxygen kind of is okay with gaining an electron, and you'll even sometimes gain 2 electrons. So our goal for this is to understand the formation of ionic compounds. And I've already kind of done that before, meaning we kind of cheated already and we showed you that ahead of time. Let's kind of take a look at it. Why do I have chapter 5 notes in chapter 6? That's just retarded. We can kind of take a look at it, you know, just straight up in terms of how those occur. So if we take a look at it, oops, we don't want to use this slideshow. We want blank slides in there. I used to try to put the pictures in the slideshow, but then I would always be running out of blank slides to write in because I could never know how many I used, and so it's just easier to tab back and forth. So formation of ionic compounds. So the idea is that if I take sodium plus fluorine, we know that it forms sodium fluoride. And actually, I'm going to be smart. I'm going to leave me lots of room to make sodium fluoride. Because sodium is 1s2, 2s2, 2p6, 3s1. Fluorine is 1s2, 2s2, 2p5. So notice that, you know, sodium wants to lose an electron. And fluorine wants to gain an electron. And we've already said that that happens, right? That sodium normally forms +1, fluorine normally forms a -1. Now we know why, because by doing so, they're left with full orbitals. With full orbitals. Another way to say that is that they have octets, or they look like noble gases. And so if I take that electron from sodium and I transfer it to fluorine, I can have NaF, where I've got this being 1s2, 2s2, 2p6, and I can get fluorine also to be 1s2, 2s2, 2p6. So they've both got those octets. Octets, full orbitals, etc. And we can use that same rationale to kind of go through all of the other types of reactions that we have too. Let's see, we showed that. Oh, so let's take a look at the energy in that reaction then. So I'll redraw the reaction. You can just kind of put it down in your notes. I've got Na plus F goes to NaF. So notice that the energy to lose that electron is simply the ionization energy. And for sodium, that is 495.8 kilojoules per mole. And if I do that same process for fluorine, it's not the energy to lose an electron, it's the energy to gain an electron. And so in this case, that is our electron affinity. And if we look on our chart, that's minus 328 kilojoules per mole. So if I go ahead and add this together, I take the ionization energy for sodium, and I take the ionization energy, or the electron affinity for fluorine. It's minus 328 kilojoules per mole. And I add them up, that's 167.8 kilojoules per mole. So this is not favorable, meaning it requires energy. Therefore, it's not likely to happen. However, here's the key. We know it happens. And we know it happens easily. So the idea is that there's a missing part of the picture. And that missing part of the picture is we have to look at the energy from forming the ionic lattice. Or what do we call that when we were talking about our Borg cube before? Did I always say lattice, I think? I thought there was one other word I used. I forget the term, though, that I was thinking of. And so what we need to do is we need to kind of take a look at that lattice energy. So we're going to define a new term. Well, we've been defining lots of new terms. Lattice energy. And that's the energy gained or lost by the formation of an ionic compound. So in this case, if I take a look at it, and of course, where do I have that written down? See, here's the bad part. Overall, whoops, wrong notes. Oh, and of course, this set of notes is for lithium. Gosh darn it, I am sometimes retarded. Where's my notes for sodium? Let's see. Do I have a table in here? There it is. Sodium fluoride would be 923. So the formation of sodium fluoride is 923 kjoules. Oops. And you guys are going to hate me for this, maybe. Yeah, so energy gained or lost by the formation of ionic compound. That's an okay definition. I really probably should define it as the energy, required to break up NAF. And the reason it's defined that way is it's easier to measure. And so the idea is that it requires 923 kilojoules per mole to break the NAF lattice. Therefore, you gain minus 923 kilojoules per mole forming the lattice. So if you take a look at that, and we go back 2 slides, if I throw in a minus 923 kilojoules per mole here, then the end result is very negative, therefore very likely to occur. So by measuring these lattice energies, by measuring these ionization energies, by measuring these electron affinities, we can actually make a reasonable prediction about whether a reaction is likely to occur or not. Now we're missing half the puzzle, which is entropy, and we'll talk about that. I think we come back to that in chapter 8 where we talk about it, and then second semester we even have an entire chapter on just entropy. So overall, what we have to do is it's a lot more complicated of a process. So let's take a look at the concept overall. There's something called a Born-Haber cycle, which is essentially says that the energy change in a reaction can be broken up into many steps whose sum must be the overall energy change. These require lots of information. And so we're going to take a second here and stop and talk about where all this information is contained in your book. Because on the, on the homework, you just look in your book. On a test, you'll have lots of cheat sheets. Essentially what I do is I copy all those pages from the book. So things that we're going to want to know are ionization energies. Oops, let's do it this way. That's E sub IE. That is contained in, let's see, table 6.2. And I didn't write down page numbers because that would have made sense. But I'll go do that now because, I'll save you guys a little bit of time. So table 6.2. Well, that was that big one we were looking at earlier. That's a good table. I like that. That's probably my favorite table in the entire chapter. It's on page 199, or 1. You're going to need to know electron affinities. That's table, let's see, where's my electron affinities? They're not in your book, so there's no table. Therefore, a given in the problem. I usually honestly steal it from a book called Chang, so don't worry about it. I will provide those types of values. There's a couple other pieces of information we need to know in order to do this, and both of these pieces of information are technically defined in another chapter, which is one of the things that pisses me off about the way your book does things. But since they cover Born-Haber cycles here, we'll also cover Born-Haber cycles here. We need to know the enthalpy of sublimation, and that is given the formula delta H sublimation. What that is simply a measure, or that's the energy required to go from a solid to a gas. And so that's on McMurray, page 246. So it's not even in this chapter. It's technically chapter 7, I think. And then we also need to know the enthalpy of dissociation. That's the energy required to break apart, for instance, a diatomic molecule in the gas phase. And so that's delta H of dissociation. That is found, oh, you're kidding me. What page? I don't have a page number for it. Oh, Jay, you sometimes kill me. Bond dissociation energies I know are in chapter 7. See, again, something mildly retarded about your book. Table 7.1, so McMurray, page 225, table 7.1. So let's see, McMurray, page 225, table 7.1. And then, of course, the last piece of information is what we were just talking about, those lattice energies. Often given the symbol U, or I like to just say delta H of lattice. That's on page 214. No, wait. Is it really on page 214? No, that's a lie. It's got to be on page 198. Table 6.3. Why is that? So this is page 198. Table 6.3. And what's on page 214? some random crap. I'm going to guess the page numbers are from my old edition of the book, and I have to update my notes to fit the new edition of the book. That would be wonderful. Also realize that depending upon where you get these values from, if you're on a different book, you'll get a different set of values. For instance, if you go to Google the answer for this question, you may or may not get the right answer because you may be using values from a completely different book or different edition of the book or a different set of tables. So realize that you need to get all that information from the McMurray book in order to get the question right. So let's take a look at that. We're going to draw a Born-Haber cycle. For the reaction lithium solid plus 1/2 F2 gas goes to make lithium fluoride solid. Now notice that 1/2 there is a bit odd in that we said you can't have half an atom, right? But I can have half a diatomic molecule if I break it apart. Now normally we would not write the reaction that way, but the way Born-Haber cycles are written is that we want to form one product. And so normally we would write 2 lithium plus F2 go to 2 LiF. But for Born-Haber cycles, we're going to be okay with using a half, and then we're also going to be okay with sort of doing it that way. And what we're going to do is we're going to write a series of 5 reactions that when added together give the above reaction. And so the nice part about having all these values tabulated is that we can figure out what the delta H of the formation for that compound is by writing a series of 5 reactions. Now I'm going to have to start this over on a fresh slide because quite honestly there's no way I can fit it on. So if you're at the very bottom of a piece of paper, just go start another piece of paper because this is rather tedious. So the very first step we're going to look at is we're going to take lithium solid and we're simply going to convert it to lithium gas. And that requires our delta H of sublimation, and that's 155.2 kilojoules per mole. So remember, sublimation is going from a solid to a gas. There, we'll make our S look like an S. I swear half the time your S's and my S's and everyone's G's all look the same, especially Zach, who has atrocious handwriting. And I got to be honest, Rodrigo's just about as bad. Okay, does that? Sorry, I probably shouldn't say names on tape like this and just call you straight out, but it's atrocious, kind of.
Oh, I don't give a crap yet.
So what you're saying is you don't give a crap when you do your homework.
No, I just do fast writing. I don't give a crap about how it looks.
Okay, so anyway, the idea is the very first step is we got to convert lithium to a gas. The second step is I'm going to take my diatomic F2 gas, I'm going to break it apart to just get one atom in the gas phase. So breaking apart an element is called dissociation, or breaking things apart. That is 1/2 of the bond energy, 159 kilojoules per mole. So notice that we only take half the bond energy because bond energies are normally defined as, you know, F2 going to F plus F, but I really only want half that. Our third step is to take that lithium gas and convert it to a lithium ion plus an electron. That's what we've been talking about earlier. That's our ionization energy. So delta H of ionization energy, that is 520 kilojoules per mole. The other thing I have to do is I have to take my fluorine gas and I have to give an electron to get fluorine minus gas. That is my electron affinity. So that is minus 28 kilojoules per mole. And then the last step is I have to take that lithium, or that, yeah, lithium plus ion plus a fluorine gas ion, and I make lithium fluoride solid, that's my delta H of the lattice. And that's equal to minus 1017 kilojoules per mole. So the idea is that if I take this reaction, just like a mathematical equation, and cancel out everything that's the same, my overall reaction should be the one I want. So notice, for instance, that I can cancel out, let's see, what can I all cancel out here? I've got lithium gas and lithium gas. I've got lithium plus and lithium plus. I got fluorine minus and fluorine minus. I got an electron and an electron. I've got fluorine gas and fluorine gas. So notice that I'm just left with that original reaction that I wrote, lithium solid plus 1/2 of a fluorine gas goes to LiF solid. And so that's the delta H of formation. And that really should be the sum of all those values, and so that should be minus 594.1 kilojoules per mole. And so the idea is that that delta H of formation is simply equal to delta H for the first step plus delta H for the second step plus delta H for the third step plus, you got the picture, delta H for the fourth step and delta H for the fifth step. So that's what a Born-Haber cycle is. It says take a reaction and break it down into each of its individual steps, and if we know the energy changes for the individual steps, then we know the overall energy change. Now, that's one way to look at it, and that's a good way with those equations, and I prefer that way to a certain extent, just because it's easy to cross things out, it's easy to keep track of the values, and it's easy to draw. The other way we can do it is we can kind of draw it in terms of an energy scale. So for instance, we can start with the energy that it takes to go from sodium, or from lithium, solid to lithium gas, and realize that takes energy. We said that that delta H of sublimation was 155.2 kilojoules. The hard part about this is it's just simply hard to write all of this in a nice, neat way. Actually, I'm going to start all over. I'm going to write it off to the side. So I've got, oh, I see how I did it. I wrote it kind of as the lines. So I've got lithium solid going to lithium gas. That's delta H of sublimation. So that takes, what did I say? 155.2 kilojoules per mole. I've got the step where I can go from, oh, I kind of like that. I like this picture. I'm going to go one more picture. This is a good picture. See, this is why my notes are good, because otherwise trying to make the picture off the top of my head is tough. So if I take a look at what I started with, which is lithium solid plus 1/2 F2 gas, then it takes 155.2 kilojoules to convert that to lithium gas, and then the fluorine gas is still the same. So maybe I'll do it like this. This is this part right here. And then it takes another 520 kilojoules to go to lithium plus gas plus fluorine gas. And then it takes, oh gosh, I don't like any of these pictures that I drew. They're all, see, I don't like the picture way. Your book has a nice picture. It's figure 6.7. It's for a different reaction, but I always have a hard time figuring out where I should put all the information. So we'll just do the, let's see. Yeah, I'll guess I'll do it this way. That way it's the right way. So here's my starting energy. This is reaction 1. And so this is lithium solid plus 1/2 fluorine gas. Then I'm taking my energy and I'm going to lithium solid plus 1/2 fluorine gas. So that was my delta H of sublimation. That was 155. Then I'm going to take my fluorine gas. I'm going to make 1/2. I'm just going to make it into fluorine gas. So now I've got lithium gas and fluorine gas. That was 75.3 kilojoules, and that's my delta H of dissociation. Then I've got lithium gas plus goes to lithium plus an electron. That's my delta H for my ionization energy. That's plus 520. So notice I keep going up and up and up in energy. Now I have to go the opposite direction. So now I'm going to go down in energy. I'm going to have fluorine gas plus an electron goes to fluorine minus gas. That was the minus 328 kilojoules. That's my electron affinity. And then I had a big drop all the way down here. That's minus 1017 kilojoules per mole. And that was my delta H for my lattice. That was going to lithium fluoride, solid. And so then notice that the missing, or that this was step 2, step 3, step 4, step 5. Notice that, and I'll switch colors, the difference in this energy level right here was that delta H of formation. And that's the minus, I can't read my own handwriting, so we'll go to the back page, 594.1 kilojoules per mole. And that really should only go down to this line right here. So notice that it's a cycle, meaning that it circles back on itself, that the sum is equal to the total of its parts. And so the type of questions you guys are going to get asked is, given this whole piece, and we'll call this step 6, you should be able to fill in any of those blanks. And I got to be honest, the only way you're going to learn how to do this is to practice and to make a few mistakes. I don't think anyone can do this off the top of their head. Even I struggle to do it off the top of my head. That's why I will argue, not a great set of notes, but a semi-good set of notes to at least look at it. Okay, let's stop there. What I'm going to say is you guys can do now homework 6B, C, and D for Wednesday or Thursday. I don't really care which day. No later than Thursday, though, because you're going to want to get those back on Monday. So really, let's just say Wednesday and make it easy. So for tomorrow, remember, you're going to finish the lab. And it really should be pretty quick, meaning that there should be lots of times for questions. So what I recommend doing is try the homework tonight, ask questions in lab. Or I also have office hours today from 1 to 3. I'll be in Striegel. And then after that, I'll come back here. Probably won't get back here till 3:15 if I have to dodge lots of zombies. So, and you know, frankly, if no one says they're going to be here, I might decide to drive to Vernal and get my oil changed. So if you're planning on coming, let me know. And let's go ahead and cancel this. And shut the lecture part off. I did print out